For decades, flying faster than sound has been a dream filled with both excitement and disappointment. When the legendary Concorde first took to the skies in the late 1960s, it seemed that the age of supersonic passenger travel had finally arrived. People imagined a future where journeys across the Atlantic would take just a few hours, and where speed would conquer the limits of distance. Yet that dream was abruptly interrupted, not because engineers lacked talent, but because of an unexpected enemy: noise. Concorde's sonic booms, the explosive double clap, created whenever an aircraft breaks the sound barrier, shook buildings, shattered windows, and disrupted life below. The sound was so intrusive that regulators banned supersonic passenger flights over land. By the early 2000s, with Concorde retired and no new planes able to meet strict noise restrictions, the dream of commercial supersonic flight faded into silence. Now, a quarter of a century later, NASA and Lockheed Martin want to revive that vision, but with a crucial difference. Their X-59 Quiet SST, short for Quiet Supersonic Technology, aims to prove something that once seemed impossible: that flying faster than sound can be quiet enough to cross continents without disturbing the people below. If this sleek experimental plane succeeds, it could change aviation regulations worldwide and open a new era of high-speed air travel. Why noise stopped supersonic travel? To understand why supersonic jets disappeared, it helps to revisit the physics. When a plane nears the speed of sound, about 767 miles per hour at sea level, it pushes against the air so quickly that pressure waves begin to pile up. At lower subsonic speeds, those waves spread out harmlessly ahead of the aircraft. But once the plane accelerates past the sound barrier, it outruns its own disturbances. These waves compress into a single, thin shockwave shaped like a mock cone. For people on the ground, this shockwave arrives as two rapid pressure changes. The result is the famous double sonic boom, a sound so loud it can rattle windows and startle entire neighborhoods. In the 1970s and 1980s, the solution seemed simple: keep supersonic jets away from populated areas. Regulators banned flights faster than sound over land, restricting Concorde to transoceanic routes. This protected cities but crippled the business case for high-speed passenger travel. A new way to tame the boom. Over the past few decades, however, engineers have developed better tools to fight the boom. Today's designers use advanced computer simulations to predict how shockwaves form and move around an aircraft. They no longer try to eliminate the boom entirely, which is nearly impossible, but instead reshape it. The idea is to stretch and soften the pressure wave so that it becomes a gentle thump rather than an explosive crack. Modern research also focuses on how humans perceive sound. Regulators once judged only by decibel levels, but now they look at how noise energy is distributed over time and how people psychologically respond to it. A sharp spike of sound can be far more disruptive than a low, spread-out rumble of the same loudness. This change in thinking opens the door for new noise standards that could allow supersonic travel over land if aircraft can prove they are quiet enough. The X-59 was created precisely to demonstrate this possibility. The plane built to change the rules. NASA and Lockheed Martin's X-59 Quiet SST is not a commercial jet but a flying experiment. Its mission is to show that supersonic aircraft can be designed to fly over populated areas with minimal disturbance. If the data proves that its quiet boom is acceptable, regulators such as the Federal Aviation Administration and the International Civil Aviation Organization could rewrite the decades-old bans on civil supersonic flights. One glance at the X-59 makes its purpose clear. Its most striking feature is an extraordinarily long and narrow nose, making up about 1/3 of the plane's total length of nearly 100 feet. This needle-like front end helps control and spread out shockwaves so they hit the ground more softly. Yet this design creates an obvious problem. The pilot cannot see forward. Instead of a traditional cockpit window, the X-59 uses NASA's External Vision System, or XVS, a sophisticated setup combining 4K cameras, synthetic vision, and flight data to create a virtual forward view. The display gives pilots a real-time augmented picture of the outside world, even in poor visibility. Supporting the XVS is an enhanced vision system from Collins Aerospace, which uses infrared imaging to help navigate in darkness or bad weather. Together, these systems replace the usual forward-facing window, a first for a manned aircraft designed for high-speed flight. To keep costs reasonable, the X-59 borrows proven components from other military jets. Its cockpit canopy and ejection seat come from the Northrop T-38 Talon, the landing gear from the F-16 Fighting Falcon, and its life support system from the F-15 Eagle. Powering the aircraft is a modified General Electric F414 engine, the same core used in the U.S. Navy's F/A-18 Super Hornet, but adapted for supersonic efficiency and quieter operation. Mounted on top of the fuselage, the engine helps keep the underside smooth, preventing shockwaves from merging into a loud boom at the rear. The plane is designed to cruise at about Mach 1.42, roughly 937 miles per hour, at an altitude of 55,000 feet. Despite that speed, its effective perceived noise level is expected to be just 75 EPNB, about the volume of distant thunder. By comparison, many modern passenger jets are certified between 86 and 95 EPNB. For a supersonic aircraft, that is impressively quiet. Years of careful preparation. Building a plane meant to change global rules takes time. NASA awarded Lockheed Martin's Skunk Works division the initial $247.5 million contract in 2018. 4 years later, in 2022, the F414 engine was installed. In 2023, the X-59 rolled out of the hangar for the first time, giving the public a glimpse of its unique profile. Throughout 2024, the team performed ground tests, including running the engine at full afterburner. Early in 2025, electromagnetic compatibility testing ensured that all onboard systems could function smoothly in real flight conditions, without interfering with each other. To prepare for future flights, NASA also tested the instruments that will measure the X-59's shockwaves. In the spring of 2025, two NASA F-15 research aircraft flew over California's Mojave Desert at supersonic speeds, gathering data in conditions similar to what the X-59 will encounter. By mid-2025, the plane successfully completed low-speed taxi tests at the U.S. Air Force's Plant 42 in Palmdale, California. It is now moving on to medium and high-speed taxi trials to check braking, stability, and sensor performance before its first supersonic flight. More than just an experimental jet, the X-59 matters not only because of its futuristic design, but because of its purpose. Many experimental planes in the past remained fascinating prototypes that never influenced commercial travel. The X-59 is different because its main goal is to collect real-world data regulators can use to redefine noise rules. Once the aircraft begins flying over selected communities, NASA will conduct surveys to gauge how people react to its softened sonic thump. Instead of guessing from laboratory tests, the agency will gather direct feedback from those living under its flight path. If the response shows that the sound is no more disruptive than ordinary city noise, regulators could finally approve new standards for overland supersonic travel. Such a change would be revolutionary. Currently, aircraft manufacturers can design fast jets, but they have no legal way to use their speed over most continents. If the X-59 clears that barrier, it could spark a new market for efficient, quiet supersonic passenger planes. Cities that are poorly connected today could suddenly be linked by high-speed routes. Long business trips could be cut in half, urgent cargo could arrive faster, and international collaboration could become more seamless. A shift in engineering philosophy. One of the most interesting lessons from the X-59 program is how it redefines innovation. During the Concorde era, the focus was on engines. More thrust, higher speeds, better fuel burn. The X-59 takes a different path by showing that aircraft shape and sound management are just as critical as raw power. Its slender nose, top-mounted engine, smooth underside, and carefully balanced fuselage volumes are all designed not to break speed records but to make speed compatible with everyday life. This approach could inspire a new generation of aerospace design where performance is measured not only in miles per hour, but also in how well technology blends with human environments. If you enjoyed exploring the story of NASA's X-59 and the return of quiet supersonic travel, don't forget to leave a like and hit subscribe. Thanks for watching, and we'll see you in the next video.